Question 15. Given that the first three terms of a geometric series are 12 cos theta, 5 plus 2 sine theta, and 6 tan theta, show that 4 sine squared theta minus 52 sine theta plus 25 is equal to 0. Well, within a geometric series, each term is multiplied by a common ratio in order to get to the next term. So 12 cos theta times r gives us 5 plus 2 sine theta, times by r again gives us 6 tan theta, and so on. This means I can write r as being equal to 5 plus 2 sine theta divided by 12 cos theta. But I can also write it as 6 tan theta divided by 5 plus 2 sine theta. Given these two different ways of writing r, I can put them equal to each other. So 5 plus 2 sine theta over 12 cos theta is equal to 6 tan theta over 5 plus 2 sine theta. Multiplying by the 5 plus 2 sine theta and by the 12 cos theta. On the left hand side I've got 5 plus 2 sine theta all squared, and on the right hand side I've got the 6 tan theta times 12 cos theta. Expanding on the left here, that's 25 plus 20 sine theta plus 4 sine squared theta. And on the right hand side, tan is sine divided by cos. So sine divided by cos times cos leaves me with sine. 6 times 12, 72 sine theta. Subtracting 72 sine theta from both sides, forming my quadratic, 4 sine squared theta minus 52 sine theta plus 25 is equal to 0. And that's what I wanted to show. Given that theta is an obtuse angle measured in radians, solve the equation in part A to find the exact value of theta. Well, if we look at the answer to part A, we have a quadratic, which can indeed be factorised. In fact, this factorises to give us 2 sine theta minus 25 and 2 sine theta minus 1. This gives us two values of sine theta we can solve for. We have sine theta is equal to 25 over 2, or sine theta is equal to a half. Of course, we know sine theta can only take a value between 0 and 1, so we discount this 25 over 2, meaning the value we wish to solve is for sine theta equal to a half. Now, we are told that theta is an obtuse angle. So if we look at our sine curve, obtuse angle is between 90 and 180 degrees. So in terms of radians, that's between pi over 2 and pi radians. So this section of my sine curve. Solving sine theta equal half on my calculator, the value I will get for theta is pi over 6. This, of course, is an acute angle, and so given the symmetry of my sine curve, pi minus pi over 6 gives me the value I want, which is 5/6 pi. Show that the sum to infinity of the series can be expressed in the form k lots of 1 minus root 3, where k is a constant to be found. So firstly, I'm going to bring in my formula book extract here. The sum to infinity for a geometric series is equal to a divided by 1 minus r for all modulus of r less than 1. Well, let's first find out what our a and our r are. So a is the first term of our sequence, which is 12 cos theta, and r we've shown previously to either be 5 plus 2 sine theta over 12 cos theta or 6 tan theta over 5 plus 2 sine theta. Here I've chosen the 5 plus 2 sine theta over 12 cos theta. We know theta to be 5 pi by 6 from part B. If we substitute this value of theta into our a and our r, we will find an a value of negative 6 root 3 and an r value of negative 1 over root 3. Substituting those into our sum to infinity formula, we have that the sum to infinity is negative 6 root 3 over 1 minus 1 over root 3. The denominator here, 1 minus 1 root 3, is root 3 plus 1 all over root 3. If we now multiply the numerator and the denominator by root 3, so we're multiplying by 1, gives me negative 18 over root 3 plus 1. I now want to rationalize by a denominator, so I want to multiply the numerator and denominator by root 3 minus 1. Doing so gives me negative 18 lots of root 3 minus 1 all over 3 minus 1. 3 minus 1, of course, is 2, so this leaves me with negative 9 of root 3 minus 1. Now I want my answer in the form k1 minus root 3. This is the same as 9 lots of 1 minus root 3, taking the factor of negative 1 out of this bracket. And this is the form that we want.